to YouTube channel Becoming a ROS Developer. Today we've got Antonia, who has just completed the course Linux Basics. So he'll be giving us a presentation on that. We'll first begin by seeing his code base running on the real robot, and then we'll get into the details afterwards. So without any further ado, I'll now hand over the platform to him so he can begin his presentation. All right.
Thank you very much.
You can go ahead. Yes.
Yeah, I'm Antonio. I'm Brazilian. And well, let's begin. I've made myself a cheat sheet of commands to run, but all these commands can be found on the Jupyter notebook of the course. So we'll be first running the connection to the real robot, which will open Gazebo and our views. Take a little while and you can command the thing.
It's alright.
And then we're going to Elias.
So right now you're working on the simulation, correct?
I'm actually connected to the real world.
All right. Can you click on the signal on, where there is that pointy with waves going out of it, right next to your real robot connection? Can you click on that so that we can see the camera?
Isn't this one the real robot live stream?
Yeah, but we cannot see the lab cameras. So if you go on your notebooks where there is the book that's open, right next to the tick with the robot head there.
Here.
Right, I cannot see your cursor. You have to go 3 steps to the left, and then after the robot head with the dot, you press that.
Real robot live stream.
That one. That's what we want to see. Yes.
Maybe if I'm presenting just Chrome, maybe if I present my whole screen, you could.
It's fine. It's fine. We want to see this screen. This is more important. That's why I was saying, can you have this one on? Maybe there.
Yes. Can you see this window that I'm?
Yes, moving? I can see it. Yes.
Yeah. This one.
Yes,
right?
That's the one I want to see. Yes.
Okay. So it is connected.
All right.
Well, going on, we must connect to the robot interface.
Oh, I see what you're doing. Okay, because you're taking commands from your.
Yes, from ID.
I see. Then it covers that screen. All right. We still have to see that somehow.
Yes, of course.
Okay.
The ID is going to be hidden after I run all the
okay.
terminals.
No worries. Okay, so you can go ahead and finish that.
Okay, so robot interface has already finished ready. That is going to that terminal there simulation is going to be reserved for future. Well, so we open now the new obstacle avoider terminal.
All right.
We'll run these lines. It will set up the workspace and start running my script.
Okay. Okay.
I'm going to increase a little bit of size so you guys can see it better. So what's doing here, so it's setting linear and angular velocity to 0 and then start iterations. So it'll read all the scan ranges around it.
Yep.
Yeah, we've done it so it reads 5 different scan ranges. So it reads front, left, right, and oh, you guys can see my cursor, right? Okay.
Yes, we can see it.
Oh, you guys can see it. Okay.
All right.
So it reads then also front left and front right. So basically 4 to 5 degrees left and right. And then it goes through a decision function that I've implemented. And it decides what's the best action, the best direction. And then it takes a decision. That decision is then fed to a action function, which then calculates what it has to do. So if it has to move forward, it calculates how much and for how long. And if it has to turn, it then, well, turns.
Right now we see that it did not turn. So what's going on? What do you think might be going on there?
Right now?
Yes.
You mean because it crashed? I don't think it actually has crashed. It just got extremely close
All
to the
right.
ball. Yeah.
And did you put any handling mechanisms for these kind of cases?
Yes.
Okay.
I've implemented some safety measures. Mainly, I've basically implemented upon a logic of percentage. So basically, it detects how far the obstacle is on the best direction.
Okay.
So on the direction that's freer, that's further from the robot, and
Okay.
then
You see that it managed to
walks only
rotate that.
25% of that distance, theoretically.
Okay. Okay. All right.
One issue that I've run that is the biggest issue so far that I've encountered is latency.
Right. I see.
When I say theoretically it should run 25% of distance, the maximum distance that's allowed.
Yes.
I mean, it should run 25 as per my code. I may show my code in a little bit, but sorry for the noise.
That's all right.
Yeah. It takes a little bit to send and receive the commands back and forth through the server and the client, mainly because of maintenance. So it may or may not walk actually 25% of the distance.
I understand that. Right now, can you explain what is happening at the moment? Is it still trying to avoid the wall? Because it seems like it has avoided the wall already and made a complete rotation. So it should be moving.
For some reason, it has frozen. This is literally the first time it has happened to me. It's never frozen before.
All right.
But so, we may check. Well, of course, the robot interface has been terminated.
Okay. Try moving it out of the corner and starting it from a different place, and let's see.
This one. So turn it a little bit. Too far. Sorry. I'm pressing K, of course. It's not gonna move.
All right. Yeah, maybe that's good enough.
Fine.
Yep.
Yeah. Do you think I should restart the robot command as well? No.
No. Just make sure robot interface is running.
Robot interface.
Yeah.
Okay. I'm just going to resource it all just for good measure.
Okay.
So we're running robot interface again. It has terminated. I must rerun this.
Okay. All right.
Otherwise it will not start. So resource it, rerun it.
That is launching your simulation. That is launching your simulation. You don't need that because you're connected to the real robot already. So you can close that completely.
Oh yes, of course. It's going to run like everything again, but I've run into some problems with the real robot if I don't actually rerun everything again.
Okay, so
it's empirical.
Let's see how it goes then.
It's fine. It's fine. This is somehow intended behavior.
Yeah, it's okay.
Oh, now the robot interface works.
Okay.
And
so you're right, it's empirical.
Yeah. Now we may quit this program that for some reason did not quit. Resource it and rerun. Do you want me to run robot statistics as well?
That'll be good. Yes, we want to see it working.
So, same thing. So these commands can also be found in the Jupyter notebook of the course. So we resource the workspace and run the robot statistics.
So this is
So it's
supposed to
getting
be
some.
supposed to be
Yes,
giving us information as the robot moves.
yes, it gets odometry data on direction, distance, position, orientation, and IMU data on angular velocity and linear acceleration.
Right. Okay.
So,
And
as you may see here, the robot has moved
okay.
a little bit.
Yes.
Not 25% as intended, but
Right.
a little bit.
All right. Can you tell me something? What did you use as your threshold? Like, what is the maximum distance that the robot has to? Okay, let's just say the minimum distance that it has to live between itself and the wall.
It has as hard-coded threshold for detection as 0.4 meters.
Okay.
But it has a different threshold for movement of 25% of the distance detected in the best direction.
Okay. Okay. So you are actually making sure that it does the computation to say only move for about leave 25%.
Yes.
All
but
right.
For reasons of latency, it does not actually move exactly 25%.
Yeah, it might take longer.
Yeah, as well as it doesn't actually turn exactly 90 degrees left and right because of, again, latency.
So right now, can you at least try to give me some information why it is stopped? Because it seems like there's still enough distance for it to move forward.
Well, it is detecting that front right is apparently the best direction because it's like 0.003 meters freer than front. So when my code, my logic is based upon a simple algorithm of just turn left, turn right, or move forward. So if it detects that the best direction is front left or left, it turns left. And also the same goes for right. And it just moves forward if the best direction is front. So you may see that it is detecting that front left is best, so it turns left. But then here it's going to detect that front left, front right is best, then it's going to turn right. So it's a little bit stuck in a loop right now.
Okay. So if you were to fix that, what would you change? What would you change in your code?
I have actually tried to implement some changes to this, but it was extremely hard to implement it, mainly because, well, what I tried to do basically was I added a new clause detecting front left and front right, and passing to the action function a different parameter, which would then try to turn the robot only 4 to 5 degrees to the respective direction.
So you were trying to limit how much the robot turns, right? Is that correct?
Yeah, so the idea was that if the 4 to 5 degrees direction was best, then maybe it would be best to turn the robot to that 4 to 5 degree direction and then move forward on that direction. But again, because of latency reasons, I could not implement 4 to 5 degrees constant and verifiable. So it did not behave as expected.
Yeah, because what I'm looking at right now is, given the specifications you're saying, right, it has managed to rotate a complete 180 degrees, right? So right now it should be able to go forward because it's all clear, right? It should not take, it should not get affected by either front left or front right, because there is a clear path in the front, right, which is like the
yes,
at the 180.
Yes, but the thing with my logic with my code is it doesn't prioritize front. It prioritizes
clearance.
Clearance. Yeah.
Right. Well, okay.
So it will always check for clearance.
Right. Again, we get back to the same question, right? It's all clear. It's supposed to move somewhere, right? Either where there is the greatest distance, and that's why I said earlier, can you move it to a different location in case maybe we might be able to get it to respond the way we want it to? So
Oh, yeah, of course.
you could try
For
move it to a different
my,
corner and let's see if it moves.
yeah, I'm going to just quit the naive obstacle avoider so I don't have any further problems. Did it quit? Tally up. Where are we? We're rotating.
Where did it get? Okay.
Wait, when is it rotating?
Maybe disconnect.
Run tally up again.
Yeah, you actually have to disconnect from the robot.
The robot interface.
Yeah.
Oh, I don't know that.
Is your obstacle avoider still running at the moment? Oh,
no, it isn't.
it's not running.
What is still running at the moment is robot statistics.
Okay, all right. So that okay, that shouldn't affect your robot. Okay, can you move it to stealth now?
I believe so.
Okay.
Yes.
Okay, let's move it to the corner. Maybe on the other side.
Other side?
Yeah, the other side, yes. And then you can start your obstacle avoider script from that corner.
Is this fine?
Yeah, that's fine.
Okay. Race forces. Rerun it. So the robot interface is ready, and I'm just running again because I don't believe it is necessary to resource it.
Okay. Okay, set angular velocity to 0. Okay. Okay.
So here it's detecting 0.812 meters on left.
On the left index, yes. Yeah.
Yes, that's probably the best action, yes. So it will turn left.
Rotate to the left, yes.
90 degrees.
Mm-hmm.
And let's run statistics meanwhile.
Mm-hmm.
So now we will surely move forward given the currents.
Yep, it is to move because the front range is saying that there is enough distance for it to move, right?
Yes.
So that this is the part that I wanted to see, and the next bit that I would like to see is can it manage to stop and at least turn either left or right?
Here it will probably go forward again because it's still a little bit far.
Okay, so
it seems to be the best direction.
All right, so tell me something. Your script, every time it runs for 25, did you say 25% of the distance?
Yes.
Yes, so it runs for that long and then it has to stop and reset parameters. Is that what's going on there?
Yes.
Oh, okay, all right, I understand. Okay.
You may see here on the log, so it says like it's approximately 1 meter and then it runs for approximately 0.25 meters.
Okay.
Then it sets that velocity based on a simple operation of division.
Okay.
For that amount of time, it sets parameters, sleeps for this amount of time, and then sets back linear velocity to 0.
All right, I see. And how did you choose 25%? Was it just a guess or did you have to try a couple of values?
Oh, no, it was extremely empirical.
Okay, so you tried so many times and realized this is what I would like. Because, okay, the general knowledge is that someone would make it move for most of the distance, right? That's what I'm thinking. So they would make it move for about 75% of the distance. You chose 25%. It seems a little bit odd for someone who doesn't really understand where it came from. So that's why I'm asking.
No, yeah.
Yeah.
What happened was actually, at first my code was meant to be for 90% of the distance,
Mm-hmm.
but then I tested and it collided, and then I diminished it to like 70% and
Yep.
it collided again,
Mm-hmm.
and then 60, and then again, and then 40, and then again.
Yeah. Okay. All right. I think this is good. We've managed to see that it avoids obstacles when it can. So it's all good. Can you just run through your code so that you get to show us some of the details? And then
Of course.
um, in about
Oh, the
5 minutes
session
or so.
ended.
Yeah.
Oh, okay. So here's my code.
Mm-hmm.
Is it, despite all the errors that are happening on my screen right now,
No, it's
is it
fine.
visible?
It's visible. Just double tap the IDE again so that it's not all
Ah,
whitey.
yeah, of course.
That's
Oh,
good. Yeah,
great.
thanks.
So this is the initial setup. Um, this is the hard threshold for detection that I mentioned.
Mm-hmm. Why did you not use
It,
point three? Um, did crash
be,
when you used point three?
um, not necessarily, but I felt like the threshold being zero point 0.4 was it prevented some rotation errors. Like
Mm.
it
Like it would touch the wall.
rotated less. Yes.
Okay, okay. So when you used point three, it ended up rotating more to avoid or to clear either the left or the right.
Yes. Yes.
Okay, all right.
I implemented a function, as I said, to decide the best direction.
Mm.
So it passes all the directions as arguments and the threshold being used.
Mm-hmm.
Um, it checks it. It checks. Well, it first starts by making the assumption that front is the best direction and it's the best range.
Mm-hmm.
And then it checks all of the ranges, comparing each one. And if it detects there is a best range or best direction, it updates the value. And then it prints what is the best direction, just for log's sake.
Mm-hmm.
And then if it detects that the best range is smaller than the threshold, then it turns left as a fallback. Um, else it will take the corresponding action depending on the best direction. If it's front, it goes forward. If
Mm-hmm.
it's left or front left, it turns left. If it's right or front right, it turns right. Um, Before it was like this. It was a bit simpler, just like using the OR statement in Bash.
Mm-hmm.
But I separated left and front left and right from front right, to implement that said turn 45 degrees left or right. But I ended up just changing it back, so I left it like this.
So what was wrong with the other method where you used or, right?
The 45, you mean?
Yes, the one where you'd consider multiple indexes, right, in the same statement or in the same.
Mainly latency. The main problem that I run into was that it could not precisely turn 45 degrees. So um,
Oh,
the logic to turn.
so you
Yeah.
wanted to reduce the number of decisions it is to make in that. Um, in
No,
that.
I wanted to increase the number. I wanted to introduce two new directions that they could that oh no, not directions, actions that it could take. It could
Oh,
turn
right,
45 degrees left or right,
right.
so it
Okay.
could be more precise. But
Okay,
I
so
could not
I see.
do that precision.
Or it could not achieve what you wanted, but you'd have wanted to I not consider five, but rather slightly more, so that it would be easier for it to choose. It would have more options to choose from.
It would be ideal, but I could not implement effectively how many degrees I wanted to turn,
Uh huh.
because even this metric here
Yes.
to turn left, which is supposed to turn 90 degrees,
Yes.
because of latency, does not turn exactly 90 degrees. It is it varies more or less between like 80 and 110 degrees.
Right. Okay. All right. All right. I see.
So, and my logic to turn like half of this amount
Mm.
was to turn for the same velocity for half the amount of time.
Okay.
But it
Still, you didn't.
basically, yeah, it turned when I introduced that change, it turned for like something between 30 and like 70 or 80 degrees.
Okay, all right.
So I couldn't precisely do that change. So I just decided that it's best to leave it as is and keep just the turn left, right, and move forward.
Okay, all right, I understand. All right.
Well, then this is the action function that I mentioned. So if it's forward, it calculates the distance between based on the distance threshold that I mentioned and the front range.
Yes.
So it prints that. It divides the move distance by the move speed to get the move time, and it sets the linear speed as the move speed set here,
Yes.
0.1, for this amount of time, for the move time amount of time.
Right. And then after that.
And yeah, and if it turns left, it just sets these parameters as is in the simple control algorithm.
Okay, I see.
And then it sets angular velocity to 0 back.
Okay, all right. I see you've got an else clause that says echo error. When would that happen? Did that work at some point? Or it was just a guard?
It's mainly just a fallback.
Okay.
Well, actually, I did manage to catch some of these errors.
Yeah.
Mainly when the node crashed.
Okay, all right. Okay, so that was really good for you to catch unknown errors like those ones. I was just curious, did it work at some point? So yeah.
Yeah. For example, when the node fell,
yeah,
when it crashed,
yes,
right here, it actually it logged an error.
Okay.
Of unknown decision, node fell, something like that.
Okay, then you would know. All right. That's good. That's good.
Yeah, and then we get the main loop. So it starts iteration, it reads all the ranges using the get scans and the functions implemented in the robot functions algorithm. I left out these commented. It was just a test that I did not really like. It was just visual, these leaps. Then it logs the second best action. It gets all the ranges and the threshold, and it logs into the side best direction. The decision, it logs decision, and it inputs decision and the front range to the take action function.
All right.
Runs and it ends the iteration. It updates the counter, sleep for 0.775 seconds, and it loops again.
All right. Thank you very much, Antonio. Unfortunately, we are out of time, but it was a good presentation. So thank you very much for taking us through what you did, how you did it, and it's quite important for us to understand, okay, did you pick these values at random? What did you do to test them to see if they are valid or not, right? And also some of the decisions you made. We want to know, okay, why 25% of the time? So thank you very much for clarifying that. So a wonderful presentation once again. So Alright everyone, this was Antonio's presentation. Warm congratulations to him, and would like to thank him for giving us the detailed explanations about what he did, why he made the choices he made, and would like to encourage all those of you who would like to give this course a try to do so, and then you can come and showcase your work here. So until next time, keep pushing your ROS learning.